Right. Okay, so today is I'm going to show you the last reminder before the quiz on next Monday. So in case any of you still miss it, by now most of you probably should have said this already. Right, so quiz next Monday, again. Okay, try to be punctual. Okay, so the quiz will be 30 minutes, conducted in these two LT, consists of 30 questions, and these are the scopes of this particular quiz here. Right, okay, attendance is compulsory, be punctual, come here at 4:30. Right, bring along a photo ID, we'll do some checking. Right, okay, bring along a calculator and a pencil, of course, eraser or any other things that is necessary. Right, in case you have not seen it before, this is the cover page of the question booklet. Right, so again, make sure that you write your name and your matriculation number on the question booklet. Right. Okay, so together with it, you have the optical form. Right, do pay some attention about filling up this part here. Course code, your name. Right, this part is important because at times it has happened before. Somehow students, just when they circle up the matriculation number, they circle it incorrectly. So for that, in order to trace it, we really need you to write your name. If you didn't write your name, we will not be able to trace you if you make a mistake. Right, okay? So on Monday, what will happen is that you'll come here, right? We'll put some question booklets as well as the optical form in the LT in alternate seats. Right, so you come here, you'll be given the time to solve to answer those questions. And later on, at the end of it, right, you bring your answer sheet, your optical form, as well as your question booklet, you come to the front. Right, we have two containers. You put your optical form in one box and your answer question booklet in another box. Is that clear? Okay. Right, okay. So for today's lecture, we are going to talk about JPEG image compression. Right, so actually JPEG compression is a little bit technical, right, because it involves a little bit of mathematics. Right, so what I'll try to do is that I'll try to give you a high-level understanding. Right, okay, so if you can understand at high level how this JPEG compression works, actually it's quite an achievement itself already, because JPEG, some of them are actually a research topic, but I try to explain in such a way it's easy to understand. Right, okay, so before we look at JPEG, we know that there's two types of a compression, as I've covered in one of the previous lecture. Yeah, there are two types of compression. One is the lossless compression. So as the name suggests, lossless compression means that no information has been lost. So what you have is that you have the original image data, you compress it into a small file size, and then you do a reconstruction or decompression. So this reconstructed image, and you compare with the original image, they are identical. Right? For lossless compression, no information has been lost. So why do you want to do this? You do this for important images such as medical images, where every single detail is important. Can you set it up? Right, okay? And also you want to avoid artifacts in the images that you have compressed. Right, okay. However, the disadvantages of lossless compression is that the compression ratio is not very high. So you will not be able to compress it into a very small file. The compressed file is still, is of course smaller than the original data, but it's still relatively big. Okay, so this is as opposed to the lossy compression. So lossy compression, as the name suggests, that means some information will be lost. Yeah, some information will be lost. So what it means is that suppose you have the original image data, you compress it, it will become a small file size. After you decompress it, right, this reconstructed image, if you try to compare with the original image, you will see that they are different now. Okay. However, this reconstructed image, a lot of the things that the information that's been lost may not be so obvious to our eyes. Actually, as far as our eyes are concerned, we cannot tell much difference between this reconstructed image and the original image. Right, so that's the whole idea. Even though you lose a little bit of information, but those information that's been lost are not so obvious to our eye. Okay, so you may be wondering, why do you want to do that? The reason why we want to go for this type of lossy compression is because usually lossy compression has a very high compression ratio. That means you can compress it into a small number of bits. So that's the advantages of lossy compression. It turned out that for most of the image and video compression, actually we'll go for lossy compression rather than lossless. Right, so next I'll give you a very quick overview of this JPEG compression. So JPEG, by now you should know, is a very popular image compression scheme or standard. That means across many platforms and software, you can readily just open it or save it as a JPEG format. It's actually officially known as the ITU-T recommendation T.81. Right, so this is a standard. For those of you who are very technically inclined, actually you can go to a library and dig out this particular standard. The standard itself is probably about the size of a book. Okay, so it's developed by this particular body called Joint Photographic Expert Group, JPEG, hence it adopts the name of the body that developed these standards here. Right, there's a few different modes of operations under JPEG. Right, so essentially there are 4 modes. One is known as sequential DCT base, okay, which is also known as baseline JPEG. For most of the JPEG image that you compress, it actually belongs to this category. Right, baseline JPEG is the most popular one. Okay, on top of this baseline JPEG, you have a few other different modes of operation like the progressive DCT, lossless mode, and the hierarchical mode. Right, this lossless mode, right, is the mode of JPEG compression where no information has been lost. Okay, but most of the time, as I mentioned, the baseline JPEG is the most dominant one. So for today's lecture, we are going to focus on baseline JPEG and try to give you a flavor of how this JPEG image compression standard works. Right, okay, so before we go into the nuts and bolts and the details of JPEG, let me just give you a very high-level overview, right, of how this JPEG works. Right, so the main idea or the operation behind this baseline JPEG is that if you given a particular image, okay, given a particular image, for natural image, right, this image usually, if you look at a small image neighborhood, the pixel value tends to change slowly. Yeah, okay, so this is the first thing you should know. For most natural images, for example, my hand, right, or whiteboard or something else, usually if you consider a small image neighborhood, the pixel values tend to change very slowly. So that is the first piece of information that you have. Right, image content tends to change slowly. So what is the implication of that? Right, if the image content tends to change slowly, that means this particular image will have a lot of low frequency content and less high frequency content. Right, if you recall what we discussed yesterday, signal then change slowly means it has low frequency content. For example, if you are talking about cloud, the smooth area, okay. For example, let me just show you. To take this particular example here, right, if you are talking about shirt or the face, right, this kind of smooth region, right, the pixel value tends to change slowly. Right, if the pixel value tends to change slowly, that means it has strong low frequency component. Okay, this is as opposed to area, for example, such as this texture region, where you have the leaf, trees, branches, the foliage region. For this region, the pixel value tends to change quickly. That means a high frequency region. But for most natural images, you tend to have more area where pixel value change slowly. Right, so that's the first observation. Right, image content tends to change slowly. That's the first observation. And then the second observation is what I've told you before. Our eyes, human eyes, are more sensitive to distortion, or we are more sensitive to low frequency component than high frequency component. Okay, so those areas then change slowly, right? If there's any distortion, our eyes can spot it very quickly. For example, today I'm wearing this striped shirt. If I'm wearing a shirt with, for example, just a single color, right? If there's a spot here, you'll be able to see it very clearly, right? Because if it's a shirt with a plain color, that means actually it's a low frequency image, right? Because the pixel values are very similar to each other. So for low frequency kind of region, if it's a shirt with plain color, if there's any distortion such as spot, your eyes will identify very quickly. This is as opposed to, for example, I'm wearing a striped shirt here. This is a high frequency, contain more high frequency information. So if there's a spot or distortion here, your eyes cannot identify or spot it so readily. So what does that mean? What it means is that our eyes are actually more sensitive to low frequency component. Okay? So if our eyes is more sensitive to low frequency component, what it tells us is that the compression technique that we are going to develop, we have better make sure that we can preserve more low frequency information, and we can afford to sacrifice a little bit of high frequency inaccuracy in high frequency information. Right? So in short, our eyes are more sensitive to low frequency component. So the idea of JPEG actually is just summarized in this particular sentence here. So JPEG make use of a frequency domain analysis known as a discrete cosine transform. Okay? And then afterwards, it will try to emphasize on the low frequency information. The reason is because our eyes are more sensitive to low frequency information. Okay? So it should emphasize on this low frequency information, and then it will perform compression using an idea called entropy coding. So it's simply that. But of course, there's a few terms here like DCT, right? This particular low frequency information and entropy coding that we need to cover quickly. So for the next few slides, I'm going to give you a very quick kind of layman overview and understanding, right? Without touching too much on the actual mathematics. Right, okay, so for baseline JPEG, it consists of the following steps, right? So the steps involved is the first step is called image block processing. So what you have is that given a particular image, if you want to compress it using JPEG, the first step is that you partition this particular image into multiple image blocks, okay? Whereas each of the image block is a 8 by 8 pixel image block. So that's step number one, known as the image block processing. The second step is called forward DCT transform. Right, okay, now I'm just going to give you a quick overview. Later on, at the appropriate slide, we're going to talk about each of the steps a little bit more in detail. So, as I mentioned, the first step, image block processing, is nothing but given a particular image, right, you simply partition it into 8 by 8 image block, right? And then afterwards, for each of the 8 by 8 image block, you are going to let it go through a mathematical transform known as a forward 2D DCT transform. Okay, so each of the 8 by 8 image block now, right, we are going to let it go through a DCT transform to map it into the transform domain. Okay, you may ask, why do you want to do this? The reason why you want to take the original 8 by 8 image block in the image domain and transform it into the transform domain is, once the data is in this transform domain, there are some good properties that we can exploit to help to perform the compression. Okay, that's the high level idea. Okay, so afterwards, once you have done the transform, this image, right, you perform 2D DCT to map it into a transform domain. Afterwards, there's still a few steps you need to do, like steps such as quantization, okay, entropy coding, and frame building. Right, those last three steps. Right, later on when we come to the appropriate juncture, I'll say a few more words about each of these steps, what they are for. Right, so this is the general overview of the JPEG encoder. So the term encoder just means that it's used to compress an image. Okay, so it's a technical term to indicate, the particular module that performs the compression. So how it works is like this. Right, this is a high-level overview. Later on, we'll go into each step to talk a little bit more in detail. Some of them is not less important. We can go through it or glance through it quickly. It's more for your information. So first of all, right, for example, if you're given a color image, you want to perform JPEG compression. What happens is that this color image is in RGB color space. Often, we'll transform this RGB color space into YCBCR color space here. Okay, the reason why we want to convert this RGB color space into YCBCR is because our eyes are more sensitive to the luminance or the brightness component. Okay, among these three channels, right, remember YCBCR is another color space. That means another way of describing color. Okay, another way of describing color. But why do you want to describe the color in this particular model rather than this model? The reason is because our eyes are more sensitive to this white component. This white component is known as luminance component or the brightness. So our eyes are usually more sensitive to this luminance component or the brightness component and less sensitive to these two color components here. Therefore, often when you perform this JPEG compression, you can afford to downsample this particular two channel here. That means instead of representing it with a larger resolution, you can reduce the resolution. Okay? The reason why you want to do that is you want to reduce the number of bits that you need to represent without sacrificing too much accuracy. Okay? Right, so suppose if you use this YCBCR color space, the next thing, as I mentioned to you, is that you're going to partition this particular image into 8 by 8 image blocks. So you're going to partition into numerous 8 by 8 image blocks. So for example, you're going to get many 8 by 8 image blocks here. So for each of the 8 by 8 image block now, you're going to let it go through a process called discrete cosine transform or DCT. Okay, so the output of this particular image block after you have gone through this DCT is that you are going to also get a collection of 8 by 8 blocks here. But it's 8 by 8 blocks of DCT coefficients. We are going to see it a little bit later. Right, and afterwards you need to let it go through a quantization process. I'll talk a bit more about it when we come to that. Right, we are going to let it go through a quantization process. We are going to let it go through a process called zigzag scanning. Right, and then this part here, you don't have to worry too much about detail. Right, just kind of assume that for this part here, you just need to go through a process called entropy coding. We'll also say a few words about this. And then finally, once you have done this, all these bits, you need to pack it into a JPEG bit stream so that when it's passed to a decoder, it will understand what are the bits that is inside. So this is a frame building process. Right, okay, so step number one, image preparation. Right, so this is just a repeat of just now the overview, except we go into each of the steps and examine it at a little bit more detail, but not too much detail, because we try to avoid the mathematics. So what you have in this particular step is very easy. Right, so suppose you have a grayscale image, or you have an RGB image, or YCBCR image. What you do is that you partition each of the image into 8 by 8 image blocks, such that you have multiples of 8 by 8 image block here. Right, so this 8 by 8 just means that this block, its dimension is 8 pixel by 8 pixel. So altogether, that means there's a 64 pixel in this particular block here. Right, and then afterwards, each of this block, you are going to forward it to the next stage, which is the DCT transform. So this part is nothing tricky. Right, so in case if you don't see it, this is again to highlight the same idea. Right, so this image block processing, what you do is given an image, you partition it into 8 by 8 image block. And one typical 8 by 8 image block may look something like this. So each of these points here essentially just represent a pixel in the image. Right, okay, so the next thing is that given the particular 8 by 8 image block, right, 8 by 8 image block, you need to let it go through a mathematical process called DCT transform. Right, okay, so you have an 8 by 8 image block. You let it go through a process called DCT transform, you'll get another 8 by 8 DCT coefficients. Right, even though I provide you with the equations here, but this is only for your information. You don't have to learn anything about this. You can just treat it like a black box. Okay, you can treat it like a black box. Essentially, what happened is that you have the 8 by 8 image block. You let it go through this particular transform known as the DCT transform. Right, also, you can call it more explicitly 2D DCT transform. You're going to get the 8 by 8 DCT coefficients here. Okay, so this is the equation to do the mapping. Right, if you want, you can also treat it like a black box. Right, just something you pop it in, you go through it. Someone else will worry about this part here. Right, but later on, I'll spend some time to go through to at least provide you with some intuition about why this particular transform is important in JPEG compression. Actually, for those of you who are technically inclined, right, I'm not sure if you learn linear algebra or those areas, you'll find that there's an important concept that you can learn. And if you can understand today's lecture, actually it's quite an achievement. Right, okay, before we go into the more, the mathematics, I thought we'll take a break first, let you relax a bit first before we go into the more mathematical manipulation. Let me just check the audio.
Happy. Okay, Michael. Okay, chill. 看着，检查向姐，来打铃，对，向姐，玻璃短，哎呦，阿媽，有冇小英？就可以晒過，睇下我佢教我哋翻嚟阿媽，呀！小 K， 打铃來，我來，哎呀，小英，向，打鈴，我來，快啲啊！OK， 咪動，哎呀，
So it just tell you, the wide angle lens really can capture very wide. So anyone in the scene, better don't interfere with the photo taking. Right. Okay. So before we start to explain or tell you the story a lot about this 2D DCT transform, right? I'm quite sure all of you know what Lego is, right? Lego. Right. So to understand why this actually. One of the most important aspects or the essence of JPEG compression, why it works, is because of this DCT transform. And so in order to also understand why this DCT transform in JPEG can offer compression, right, we need to learn a little bit about this Lego. Right, so everyone knows about Lego, huh? Right? So for the next few slides, I will require you to use your imagination a little bit. Huh? Right, okay, so this slide here is more for your information. You don't have to worry too much. This, for DCT transform, associated with it, there's always something known as a basis function. Okay, so this is the basis function that is associated with a JPEG compression. Right, just take it as it is now. You don't really have to worry too much. You don't have to memorize anything. This is just for your information. For JPEG compression, together for DCT transform associated with it, there's what we call this basis function. This basis function is nothing but the collections of Lego pieces that you have. Right? You can kind of imagine this. In this case here, what you have is that you have 8 by 8. That means you have 64 pieces of Lego function. Okay? This set of Lego function consists of this 64 different types of pieces. Right. Now, how do you interpret each of these pieces here? Right. Okay. Because this one is 8 by 8, so it's a little bit harder for you to visualize. So I make it a little bit easier. I'll try to reduce it a little bit to a 4 by 4 DCT basis function. So for this case here, I'm going to restrict to 4 by 4 only. Right, but for JPEG, bear in mind, actually it's 8 by 8, because early on, if you can remember, what we have is that for DCT transform, you have an 8 by 8 image block, right? So you perform the DCT, you are going to get a 8 by 8 DCT coefficient. So together with this 8 by 8 image block, you have the 8 by 8 DCT basis function. But to help you to visualize or to understand the essence of this DCT, why DCT can achieve compression in JPEG, right, we consider 4 by 4. Okay, so this is a 4 by 4 DCT basis function here. Right, so first of all, we need to understand what is this thing trying to say. Right, the first thing that you should try to imagine is that these pieces of things here is nothing but your Lego function. You have a collections of Lego functions. Right, so for these Lego functions here, you have altogether how many different types of it? You have 16 different types of Lego function, 16 different types of pieces of Lego function. And then how do you interpret it now? For this particular first type of Lego in your Lego collection here, right? So the first one here, how we interpret this kind of graph is like this. If it's bright, okay, that means its value is large. If it's dark, that means its value is small, okay? So this particular piece here, you can kind of imagine is nothing but if your Lego function just simply have a flat value, Right, the second types of Lego function that you have is something like this. Right, you can see this value is bright and this value is, is bright and this is dark. What it means is this value is large and this is small. So if you take a knife, imagine if you cut it through, what it means is that the profile is changing from large to small. Okay, large to small. Right, so likewise now, if you look at this, this one means that large, small, small, large. That means now, if you cut it through, it's large, small, small, large. Okay? And then finally, this one is right, even moving faster here. So what do you notice is that as you move across this domain horizontally, the pieces initially is flat. Yes. The second one is changing slowly. The next one is changing faster. And the third one is even faster now. Okay, so as you move across it horizontally, you can see that horizontal frequency become faster and faster. So by the same token, if you move it down, you can also imagine the same thing happen. This piece here is flat. Okay, this piece is flat. This piece here means that, right, large, small, yeah, something like this. Okay, large and small. And this one means large, small, small, large, small, small, large. That means it's moving faster and faster. So you can see as you traverse down, right, the vertical frequency becomes faster and faster. Okay? And then for this direction, if you move it, that means the pattern actually will change much faster in a diagonal manner. Right, so in short, what you have now is that what I've explained to you is nothing but, imagine now you have a new, now you are in university. I give you a new set of Lego function. This Lego function looks a bit more complicated, right? So you have these 16 different pieces, right, with those kind of different types of pieces you have. Are you able to imagine that? Yes, huh? Okay, so the part is still okay. So let me just tell you a little bit now. I actually just need about 2 more slides, and then the story will be there. So. So the idea of DCT transform, if you don't touch the mathematics, it's actually not difficult to understand at all. Right, just imagine that, suppose you have this particular, let me see here, seems to be off a little bit. Right, okay, the idea of DCT transform actually is not too difficult to understand. Just imagine that for one moment, suppose you have a 4x4 image block. For one moment, assuming that you have a 4x4 image block that you have, this 4x4 image block is shown as here. Right, suppose this is a 4x4 image block. Suppose I only write down a few numbers. So for this image block, the first pixel here has a value of 2. This pixel here has a value of 1, this pixel has a value of 3, and this pixel has a value of 4. The rest of the pixel value I don't bother to write down because otherwise I'll be spending lots of time to draw it. So essentially, what you have to do is very simple. In exercise number 1, right, imagine if you are in primary school, what you are given is you're given the first sets of Lego function. Right? This first set of Lego function is very simple. It consists of things like this. You have 16 pieces of them. But the first piece that you have is something that looks like this. It has a value 1 here and is 0 everywhere else. Can you imagine that? It's very straightforward. Huh? The second type of Lego function in your collection 1 that you use in, say, primary school, it has a value of 1 here and 0 everywhere else. Right? And then you have the third piece here. By the same token, you can imagine the third piece, that means that you have a value 1 here and then the rest are all 0. But I didn't bother to draw all of them out, so I leave them empty here because I just need a few to demonstrate the idea. Right, so the fifth one that you have here has a value 1 here and then 0 everywhere else. Right, and then the fourth one, you have a value 1 here and 0 everywhere else. So you can see these sets of Lego functions appear to be very trivial, right? Appear to be very trivial. You just have a value 1, the rest are all 0. Okay, so it's true. This particular set of Lego functions, set number 1 is actually very simple. Now the question that I want to ask is like this. Suppose you have this particular image block here. Okay, can I ask you how many pieces of these types of Lego function is required for you to reconstruct this image block? How many? How many? How many? 4 by 4. This is 4 by 4. All right. How many pieces of this type of Lego function is required for you to reconstruct this image block? 16. Yes? I hear 16. I hear 2. All right. Earlier on, I have actually shown you 2 out of these 16 different types of Lego function. I've shown you 1, 2, 3, 4. But by the same token, you can imagine easily what the other 12 pieces will look like, right? Okay. So now the question is very simple. Let me just put it again. All right. So what you want to do is that you want to reconstruct this particular image block using these collections of Lego function that you have. Right. So now, with respect to this particular example here, how many pieces of these types of Lego function do you need to reconstruct this image block? How many? How many? Right. Okay. 16. No. How many pieces of this type? This type only. This type only. You know, when you play Lego, there's a long one, there's a short one, there's different type, right? So now I'm talking about with respect to these types of Lego function. How many do you need to reconstruct this image block? You need. I just now among what I heard, I have heard 2, I've heard 4, I've heard 16. Actually, one of them is correct. What is it? 2, right? It's quite obvious, right? It's 2. Yeah, it's so obvious that, okay, because among all these Lego functions, there's only one type of Lego function. You have a value 1 here. Am I right? Okay, so if you want to reconstruct this value 2 here, you must use 2 pieces of this. Correct? It's not rocket science. But anyway, now let's continue on because I need to complete at least this part of the story by today. Yeah? How many pieces of this Lego function do you need to reconstruct this? 1, huh? All right, okay. How many pieces of this type of Lego function do you need to reconstruct this image block? 3, yeah? Right, and then this one is 4. Okay, so what's the moral of the story here? Because some of you suddenly will think, no, well, it's so trivial. I mean, why on earth do you want to even tell you about this story? Right, okay, the reason why I want you to tell you about this story is like this. Because given any image block, okay, if you just think about this image block, for many of you will just imagine, okay, what you have is nothing but, right, okay, you have a 4 by 4 image block, and then you have some pixel value on top of it. That's it. But actually behind this, there's a scene, there's a story you can tell. What you can tell is that you can always say that this particular 4 by 4 image block actually can be built based on a collection of Lego function. And the first Lego function that you have is these types of trivial Lego function. So these types of 16 pieces of these types of Lego function that you have, whereas you only have a value 1 here and the 0 elsewhere. This is the first Lego set that you play with when you are in primary school. Okay, it's very easy. Right, I give you any image block, you should be able to reconstruct it easily once you have found out how to do it. Right, the next thing is, okay, so what I want to tell you in this case is that behind this particular scene, that means given any image block, you can always associate it with a collection of Lego function. Okay, behind every image block, you can always associate it with that I can use a Lego function to reconstruct this image block. Okay, now, the interesting thing now is that suppose, given this particular same image block now, the question is, given this particular image block, Right, if I want to reconstruct using this Lego function now, okay, this Lego function now is actually more complicated now, correct? So this is the Lego function you're supposed to play with now in your university, right? So, but the same idea actually applies. What it means is that, okay, given this particular exactly the same image block, right? Okay, when you're trying to perform or find out the DCT transform, essentially what it's saying is this: given this particular image block, tell me how many pieces of this is required for you to reconstruct this. And the number of pieces that's required to construct this image block is known as S00. Let me just call it S00 for one moment. Okay, the number of pieces that's required for this. Right, how many pieces of this is required for you to reconstruct this image block? The number of pieces that's required, let me call it S01 for the time being. Right, of course, you can use the imagination to see that there's two more items here that correspond to this one and this one, correct? Next, how many pieces of this Lego function is required for you to reconstruct this image block? The number is S10. Okay, by the same token, you should be able to, if I want, you can write down all those 16. Okay, so now, what is the significance of these particular things here? Right, how many pieces of, what's the significance of how many pieces of this Lego function, how many pieces of this Lego function, and each of them is required? Okay, it turned out that the number of pieces of this Lego function that's required for you to reconstruct this particular image block is the DCT coefficient. Okay, so, right, let me summarize. Essentially, when you are performing DCT transform, there's two ways you can look at it. Either is you can just think about it as just now the equation. You have an image block, you let it go through a black box, right, some mathematical operation, and then you have suddenly the DCT coefficient already. That's one way you can do it, but if you spend a little bit of time to think about it, actually there's another way you can look at this DCT transform. And how you look at it is simply like this, as I mentioned. Given a particular, for example, 4x4 image block, where I perform the DCT transform, essentially you can see a 4x4 image block means that I'll get 4x4 DCT coefficient. But how do you interpret each of those DCT coefficients? Right, okay, each of these DCT coefficients you can interpret as nothing but how many pieces of these types of Lego function that is required for you to reconstruct this image block. Okay, again, after I tell you actually, no, that's another alternative way of interpreting DCT. I'll tell you how you can interpret DCT by simply saying, okay, how many pieces of this kind of Lego function is required, okay? So for some of you, you will still be thinking, why do I want to do this exercise? It seems that, no, it's pointless, right? Whether I represent this particular image in this kind of Lego function, which is easier, or I represent this image in this kind of Lego function, which is more complicated. No, it just looks a bit a mathematical challenge. What's the point of doing this? Right, the point of doing this is that, right, okay, which is where the beauties of this DCT is that, right, you remember, okay, before I even tell you the story or the motivation, now, I just want to test whether some of you actually can gain some insight into this already. Suppose I have an image block, a typical image block. If I perform DCT transform, by now you can see there should be a 4x4 coefficients here. Can you tell me whether the coefficients near this region here will be larger or coefficients near this region will be larger? Coefficients near this region will be larger or coefficient near this region will be larger? Or to rephrase it, what it means is that, do you think that when I reconstruct an image block, a typical image block, do I need more these types of Lego function or more these types of Lego function? That's the question. One or two? Okay, five is a little bit beyond me. I probably have to come back a few years to answer that. Right, okay, whether you need more pieces of Lego function from here, or you need more pieces of Lego function from here, okay, to reconstruct a typical image block. 4x4 image block. Which one? One, let me just get a few. Right, one is that, answer one is you need more of these types of Lego function. Okay? Answer 2 is you need more of this. So who think is 1? 1? Okay, I see a few hands, probably just less than 5. Right, okay, let's see, 2. Right, okay, why do you think, okay, actually about the same, another 5. So the rest, again, is, right, probably is 3. Right, but anyway, for those students who answer 1, why is it 1? Why do you think it's 1? Why? If you can answer this question correctly, actually, you pretty much gain the essence of, the mystery behind this JPEG. And actually, the way I see it is quite an achievement, right? Because this JPEG compression, some of them is a research topic for some PhD students. Whereas you can understand within one lecture, it's quite an achievement. So, yeah, why do you think it's 1? If you can answer that question properly, you more or less has already understood the essence of how JPEG works. Why do you think? Okay, for some people who say 1, right? Why? Why? Actually, if you remember, in the very early beginning of the lecture, I already told you the answer. Yeah, somehow among all those things I said, there's one thing that answers the question. Yes, anyone? Anyone? Okay, if you don't say 1, okay, 2. Why do you think that, for those who answer 2, why do you think you need more pieces of these types of Lego function to represent a typical image block like this? Yes? No idea? Right, there's actually, earlier on I mentioned to you, right, given a natural image, if you look at a natural image, right, usually its pixel value, how does it change? Its pixel value tends to change. Change what? Slowly, right? So if the pixel value tends to change slowly, do you think you need more of these types of Lego function that change slowly, or do you need more of this type of Lego function that change very quickly? You need more of these types of Lego function that change slowly, right? So that's actually the essence of DCT transform is actually when you perform this transform, right? Given this particular image block here, if you are just given a particular typical image block, you do not know what is the likelihood of all this pixel value. Each of the pixel value has an equal chance of being large or small. Correct? If you are just talking about typical image block, each of the pixel value here has an equal chance of being large or small. But once you perform this transform, you transform it into a DCT domain. What you can tell for sure is that for most of the natural images, these values here are going to be very large, and these values here are going to be small. Okay, why? It's because most natural images tend to change slowly. If they change slowly, that means you need more of these types of Lego function than these types of Lego function. Right? So in other words, that means the coefficients near this region will be very large, and the coefficients near this region will be very small. Again, why is it important? Right? The reason why it's important is that if the coefficients near these regions are very large, the coefficients near these regions are very small, that means now I can focus my effort, right, to only encode or represent these types of coefficients near this region. And by the way, this particular process is known as an energy compaction, because in the spatial domain, the pixel value, each of the pixels can either be large or small, equal chances. But once you transform into here, most of the coefficients near this region will be very large, right? Energy is nothing but the value you squared. So now the energy now is packed into a small number of coefficients. So the good thing about you pack energy into a small number of coefficients is, right, you only need to dedicate your limited resources to represent data in this region. You don't have to worry too much about the other region already. Right, so that's pretty much the most important point. Right, so the next few slides is actually just a recap right, of what we have. It's just a recap of what I've spoken earlier, right, except I put it in a slides form. So essentially what I told you before is, given an 8x8 image block, right, earlier on the example is 4x4, huh? But now we have to, for JPEG compression, it's 8x8. So your Lego function now is a little bit more complicated now. You have 64 pieces. Okay, so what you have, as far as the DCT transform, is depending on people, right? If you can understood, you'll be the best. If not, it's still okay, right? So the DCT transform is nothing but this, right? Given an 8x8 image block, you perform DCT, you'll get 8x8 DCT coefficients. Okay, by convention, this term is known as a DC coefficient. The rest are called AC coefficients. That is not too important. So anyway, what I'm trying to say is, for those of you, if you don't quite get somehow the idea, it's also okay. Doesn't matter. What you have, DCT transform is this 8x8 image block. You let it go through a mathematical mapping, like the equation that I've shown you. You can think of this as a black box, or somehow you just come out with an 8x8 coefficient. But for some of you who somehow managed to get the idea, right, essentially when you're calculating DCT transform, what it means is that to reconstruct this image block, how many pieces of each type of this Lego function is required. And the number of pieces that is required, you just write them down accordingly. That is the DCT coefficient. And you, by now you should also understand, given a typical image block, you need more these types of Lego function than this type of Lego function. Because this type of Lego function change slowly, this type of Lego function change quickly. So therefore, you expect for most typical image block, right, the DCT coefficient near these regions, okay, which is known as a low AC, this is a DC and this is a low AC region, this is the high AC region. So the coefficient near the low AC regions are going to be larger than this, okay? And this particular observation is also known as energy compaction. Right, so I give you one particular image block to further demonstrate this idea. So you can see this is the image block in the original domain. So this is the DCT coefficient, okay, after the transform. So what do you notice? You notice, for example, for this particular image block is corresponding pixel value. Huh? Each of the pixel value has an equal chance of being large or small, large or small. So if you are given image in this domain, you really do not know which are the pixels I should really put in my effort to represent them. But once you transform it into the DCT domain, you can see that now values near these regions are large. Values near the rest of regions are very small. So now I know I can reserve most of my resources to coefficients near this region. Okay? So that's actually the main idea of DCT. Right? This graph further, again, it's just the same message but shown. Right? So this is the DCT coefficient. So the DCT coefficient, as I mentioned now, this coefficient means that how many pieces of this type of function is required. This coefficient means how many pieces of these types of Lego function is required. Except in this case here, I actually plot the 3D graph rather than just now it's a 2D gray level. You need to help you to visualize. Do you follow what I'm trying to say? Okay, so it's the same thing. Right, so to summarize, what's the good thing about DCT transform is because for DCT transform, it converts the data from a form into a form which is more suitable for compression, right? In the original 8x8 image block, the pixel value you do not know is equally likely to going to be large or small. So this one is difficult to compress it. But now, after you perform DCT, we know that now only the values at certain region are large, the rest are small. So we can dedicate our resources to only represent those small number of pixels. Right? So therefore, high level means that it converts the data into a form which is more suitable for compression. Right? Okay, this sentence here is not so important. So yeah, but anyway, I'll just say it. Right? It reduces the correlation between the pixels. Okay? Right? And then this transformation also achieves energy compaction. So energy compaction means now the energy are all packed into a small number of coefficients, and when we can dedicate the rest of the resources to that. Right, okay, let me see. Yeah, I just have one more slide and then I'll take a stop here. Right, so this is the 8x8 image block. Right, the detail you don't have to know so much. Just simply, this slide is simply trying to show if you have 8 by 8 image block, after you perform 2D DCT here, right, most of the energy now will be compact here. That means the coefficient near these regions are very large. The coefficient near these regions will be small. Okay? And on top of that, this coefficient is known as DC. The rest are called AC. And this region is known as low AC because it's changing slowly. So we call it low AC, and these are known as a high AC region. Okay? I think we'll stop here. I'll see you next week during the